This basic design to generate a pulse width modulated signal allows us to control the R, or the resolution, and it also allows us to control the duty cycle, let's call it D, which is in here. However, it actually suffers a couple of problems in here. The first of which is actually the frequency, the pulse width modulation frequency, which I called PWM. So according to this design, this design actually operates at the system frequency, because we usually connect anything that needs a clock to the system clock. So there's no way for me using this particular design to change the frequency of the pulse width modulation. You might argue that I can change the number of bits it actually counts in here, and eventually I'll be changing the basically the frequency. But if you're doing this, you're actually changing the number of bits, which is R, and you're changing the resolution, which is something a little bit separate, and I want to deal with it separately. So we need to add or improve this design a little bit so that we can control the frequency of the pulse width modulated signal. And the solution for this particular problem is pretty straightforward, actually. So according to synchronous design principle, everything should be connected to the system clock if you're actually designing in a synchronous circuits. So I should not be operating these with different clocks. So in order for me to change the time that actually this particular counter actually change its count, we should add just a Prescaler Counter, which is just a different counter that does exactly the same thing, but instead what it does is actually outputs a tick at a very specific period of time, and that tick is actually connected in here, and it enables the second one. So the Prescaler is what's going to allow me to control the different frequencies. So as you will see shortly, that I will be just adding another counter in here. We're going to call it the Prescaler Counter. Okay, and that Prescaler Counter ticks at a very specific period of time. These particular periods of time will actually allow me to change the F or the frequency of the pulse width modulation. Okay, the second problem in here is the following. So now I can definitely see the duty cycle in here. I can definitely now, after I add this, I will figure out the pulse width modulation. However, let's see, when does the pulse width modulation output gets outputted as 1 and when is as 0. So the duty cycle in here can be calculated as following. So you go from 0, let's say the R is actually 1 divided by, or let's say R is 8 bits in here. So it's 0 divided by 256, and then 1 divided by 256, all the way to depending on whatever duty is. And if it's duty, it's actually duty, let's say divided by 256, and that's it basically. So if this particular number, which is here, is exactly at that particular value in here, and before, the output of the signal would be exactly at 1. Once you reach that particular value, and it's actually specifically duty minus 1 because it's exactly greater than or less than. Okay, I'm not comparing when it's equal. So when it's equal, I don't care about it. So since we have the duty in here, so what we have is duty minus 1 divided by 16. And if you think about it, then it continues all the way here at 0 from duty divided by 256 all the way to hopefully 256 by 256. So the issue is the following in here. So this particular here, I have duty numbers because between 0 all the way to duty minus 1 is actually duty. So the duty cycle for this particular signal would be duty divided by 256. So the issue is the following. I will never be able to reach 256 divided by 256 because duty in here is defined to be 8 bits. And if it's 8 bits, that means it will only have 200, like the maximum value you can reach is 256. Okay, so what we need to do is we will just need to add another bit in here. So instead of being R, I'm just going to say it's R plus 1 bits. And the reason why is because I want to be able to provide that this duty can be 256. Okay, so that I will have or reach 256 divided by 256 and we get the 100%. So the first issue with there's no way to actually provide the frequency for the pulse width modulated signal. The second issue is actually the duty itself in here. I will never be able to reach 100%. So now I will be able to reach 100% if I can allow duty to actually increase by 1. So I'll be able to provide duty as 256. And these are the 2 improvements I should add. So in here, I want to talk a little bit about this this particular concept of actually the system frequency and how we do it. So in terms of the frequency of which, if I actually take the basic design and I just follow the frequency and nothing else, and let's assume that the system frequency is F system, and we figured out that the number of bits for this particular register is actually R bits, That means for every 2 to the power r clock cycle, it's actually generating one pulse width modulation period, because this actually goes all the way from, basically it's set to 1 and then goes to 0 all the way to 0, and it's exactly between 0 all the way to 2 to the power r minus 1. So in total it's 2 to the power r cycle. So I can figure out the pulse width modulation signal just as simple as saying, well, it is the system frequency divided by 2 to the power r. And that's basically the one here. So in our example, we're operating at 100 megahertz. Let's assume that we decided that the resolution is 8-bit. That means the pulse width modulation signal I'm generating using this particular design is set to 390 kilohertz. Again, if you take a look at this particular equation in here, the only way for you to change that pulse width modulation signal is by changing either the system frequency, which generally you can't, or the resolution. But if you're changing the resolution, you're changing also the resolution and duty cycle and everything. So the solution to that is, instead of using the F system, I'm just going to use a Prescaler Counter as we mentioned previously, and that one will actually change that F system, and instead of dividing by F system, I'll divide it by some sort of a divisor. The same goes in here. So this one here, you can think about it as a divisor. So the whole thing in here, it's actually just a slower frequency. So this one here is a slower frequency, and it's based on that divisor. So what we need ultimately is to be able to figure out the pulse width modulation, or the desired pulse width modulation frequency, and it is that which is the F system, which is the 100 megahertz divided by a divisor and 2 to the power r. Frankly speaking, what you really care about is actually the divisor, the number. You will have your system frequency, you'll have the resolution, you'll have to actually enhance the pulse width modulation frequency. You just need to figure out the divisor. And later on, you'll see that the driver will actually use this particular equation to figure out the divisor based on what is the ultimate frequency you want your pulse width modulation signal to operate at. Okay, so let's take a look at the enhanced design. So the enhanced design is pretty straightforward. It's very, very similar to the basic one, except for that I will add another counter in here. So you take a look in here, you will see that I have the D register, the pulse width modulation, and now I have the prescaler in here. So that one here is the prescaler. Okay, so the prescaler, and you take a look at it, it's basically, I have 3 register, the D register in here, which is a counter, the pulse width modulation in here, which actually just to avoid glitches, and now I have a prescaler, which is not shown on the basic design. So let's take a look at how that prescaler operates. The prescaler is based on some sort of a divisor. That divisor is now an input to the whole module. Okay, and the divisor, again, we compute it using here based on the frequency that I care about. Okay, and then it's just a modular counter. That's basically it. So what I'm adding here is a modular counter that actually ticks exactly when I want, basically based on the divisor. And the rest of it now instead of just operating all the time at DNX, which is here, instead of just adding all the time based on the system frequency, it's just adding whenever tick, exactly at the tick. And this here is an extended actually D. What I'm doing in here is I'm extending this. Let's assume that it's R, which is equals 8. I'm just basically extending it to make it 9-bit. Okay, and I'm extending it by just attaching 0 to the most significant bit. And the reason why is because now my duty is, instead of being R bits, is actually R plus 1. 0 to R is actually R plus 1 bits. So I added another bit just so that I can get the 256 in here, and that's enhancement. So the enhancements is really pretty straightforward. Change this R minus 1 to R, add a prescaler in here, and of course add a divisor to control that prescaler.